Good morning and welcome to all of you. Today we are going to discuss about the energy density in electrostatic field. Energy density means energy per unit volume. Suppose in a region you got a system of point charges. Let us say n number of point charges are placed in that particular region. What is the energy of the system containing n number of point charges? In order to obtain an expression for the energy of the system containing n number of point charges, let us consider what is law of conservation of energy. According to law of conservation of energy, energy can neither be created nor destroyed, but it is always possible to transform one form of energy into another form. Like for example, in the case of fans, ceiling fan, electrical energy is converted into mechanical energy. So it is always possible to transform one form of energy into another form. But as such, energy can neither be created nor destroyed. For example, let us consider there is a ball placed on the ground. I want to lift this ball against the gravitational force, and to place it at a height of h meters above the ground, I have to spend some energy. Because energy is constant, whatever energy I have spent in placing this ball at a height of h meters above this ground is now preserved in the form of potential energy. If I release my hold on this ball, what happens? It falls down. So whatever potential energy it has got, it gets converted into kinetic energy. Now here, we want to find out what is the energy of the system containing a number of point charges. So because energy is constant, whatever energy I have spent in placing these n number of point charges at the respective places, that would be preserved in the form of a potential energy. So energy of the system containing n number of point charges is nothing but the energy that we have spent in placing these n number of point charges at the respective locations. So as long as these n number of point charges are placed at the respective locations, the system will have a potential energy. Once we release hold on these n number of point charges, what happens? Because all are positive charges, there will be a repelling force acting on these positive charges. So each point charge will try to run away from the other charges. So whatever potential energy the system is having, it gets converted into kinetic energy. So now let us once again focus on how to find out the energy of the system containing n number of point charges. So for that, initially, let us assume that we got a vacuum free of charges. So naturally, electric field intensity initially in that particular region is 0. In order to place Q1 at point 1, what is energy that we have to spend? It is going to be 0, because the expression for W is equal to minus Q integral E dot dl. Initially, because it is vacuum, electric field intensity is 0. So the work done to place Q1 at point 1 is equal to 0. But once we have placed Q1, at every point there will be electric field intensity created by Q1. Now, if I want to place Q2 at point 2, naturally Q1 will try to repel Q2 in this direction. So against that force, if I want to place Q2 at point 2, I have to spend some energy. What is energy that we need to spend? It is equal to Q2 into V21. Work done to place Q2 at point 2 is equal to Q2 into V21. What is V21? V21 is a potential at point 2 created by the charge Q1. Suppose if the distance is R12, between 1 and 2 the distance is R12, V21 is equal to Q1 by 4 pi epsilon naught R12. The potential at point 2 which is created by Q1. Now if I want to place Q3 at point 3, both Q1 and Q2 will be repelling this Q3. Against these repelling forces, I have to place Q3 at point 3. So now what is the work done to place Q3 at point 3? Q3 into the total potential at point 3 because of Q1 and Q2. So V31 plus V32. Like that, if I place n number of point charges, what is the total work done? Q2 into V21, Q3 into V31 plus V32. Similarly, Q4 into V41 plus V42 plus V43. Like that, it goes on. So, for placing n number of point charges in a region, this is the total work done. Let me represent this as WE. Now, if you look at this Q2 into V21, this is Q2 into what is V21? The potential at point 2 because of the charge Q1. So, Q1 by 4 pi epsilon naught R12. If I interchange Q1 and Q2, I can write this as Q1 into Q2 by 4 pi epsilon naught R21. What is Q2 by 4 pi epsilon naught R21? It is a potential at point 1 because of the charge Q2. So, when we have got Q2 into V21, it is equal to Q1 into V12. Like that, suppose you have got Q3 into V31, it is equal to Q1 into V13. Q3 into V32, it is equal to Q2 into V23. So, when we rewrite the expression for WE also can be written as Q1 into V12 plus Q3 into V13, so Q1 into V13 plus Q2 into V23, like that. So when I add these two series, WE, we have got two different expressions for the same WE. This is one expression, this is another expression. Now when I add these two, 2WE is equal to Q1 into, now let us arrange the terms, okay, in this particular way. Q1 into V12 plus V13 plus V14, like that, V15, so on. What is the last one? V1n plus Q2 into V21 plus V23 plus V24, like that. V12 plus V13 plus V14, etc. What is this one? It is a total potential at point 1 because of Q2, because of Q3, because of Q4, and last one is because of Qn. So this is the total potential at point 1 because of the remaining point charges Q2, Q3, Q4, and so on. Similarly, what is this one? V21 plus V23 plus V24, etc. This is the total potential at point 2 because of the remaining charges Q1, Q3, Q4, etc. So if I represent this as V1, the total potential at point 1 because of the remaining charges Q2, Q3, so on. This is V2. Capital V2 is the total potential at point 2 because of the remaining charges Q1, Q3, so on. Okay. So now 2WE becomes Q1 V1 plus Q2 V2 plus Q3 V3, so on. The last term is going to be Qn into Vn. So I can write this as WE is equal to 1 by 2 sigma Qm Vm, m is equal to 1 to n. Suppose you have got a finite number of charges like for example 3 or 4 point charges are placed, then I can make use of this expression. It is something like suppose there are 3 points. 1, I'm placing Q1. At point 2, I'm placing Q2. At point 3, I'm placing Q3. So 2WE is equal to Q1 V1 plus Q2 V2 plus Q3 V3. What is V1? The total potential at point 1 because of Q2 and Q3. What is V2? V2 is the total potential at point 2 because of the remaining charges Q1 and Q3. What is V3? Total potential at point 3 because of Q1 and Q2. So like that, if the number of charges is finite, I can make use of this equation. But suppose I got a tremendous number of point charges, then the sigma Qm can now be replaced with the integral rho v dv. Suppose you got millions of point charges, how do you represent the charge in the form of a volume charge? So we know that integral rho v dv is equal to q. So if the number of point charges are very large, then sigma qm can now be replaced with the integral rho v dv. So we becomes 1 by 2 integral rho v vm dv. Now this vm has no significance. Integral rho v into v dv. So this is the expression. And we also know that del dot d is equal to rho v. So in place of rho v, I can substitute del dot d. We is equal to 1 by 2 integral del dot d into v into dv. So we have this vector identity. Suppose A is a scalar quantity, B is a vector quantity. Divergence of A into B is equal to A into divergence B plus B dot grad A. So divergence of V into D, suppose V is a scalar quantity, D is a vector quantity. So when you apply this one, it becomes V into del dot D plus D dot grad V. So when I write an expression for del dot D into V, it is equal to divergence of Vd minus D dot grad V. So let us go back here, del dot D into V. Now it can be replaced with the divergence of Vd minus D dot grad V. So We becomes half integral divergence of Vd into dV minus 1 by 2 D dot grad V dV. Now applying divergence theorem, suppose you have got integral d dot ds is equal to integral del dot d dv. This is what is known as divergence theorem. So whenever there is a closed surface, it defines a volume. The relationship between the closed surface integral and the equivalent volume integral is defined by a divergence theorem. So when we have got integral del dot d dv, what is equivalent surface integral? Closed integral d dot ds. Now when you apply this divergence theorem, integral divergence of vd dv. So when you write this as a closed surface integral, closed integral vd dot ds, okay, that's minus of grad v is equal to e. So plus 1 by 2 d dot e dv. Now this integral approaches 0 at the rate of 1 by r because v is inversely proportional to r, d is inversely proportional to 1 by r, is proportional to 1 by r square, and ds is proportional to r square. On the whole, this term approaches 0 at the rate of 1 by r. So neglecting this term, you are left with WE is equal to 1 by 2 integral d dot E dV. Suppose if I differentiate both sides, dWE is equal to 1 by 2 d dot E dV. dWE by dV, that is what is known as the energy density. Energy density is equal to 1 by 2 d dot E. And we know that d is equal to epsilon into E. So 1 by 2 epsilon magnitude of E square into dV, that is energy density.